Okay, in this example, we're going to examine a proton transfer membrane. And this is a very narrow membrane channel depicted in here. It's so narrow that water molecules can only form hydrogen bond networks in single file. And at some point along the water wire running down the center of this channel, you'll have a proton sitting there. Now that proton could sit on the site here, 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 or here. The proton prefers to be in the bulk water at either side of the two ends of the membrane because it can be solvated in 3 dimensions with all 4 hydrogen bonds to the hydronium fulfilled. When it's in the membrane channel, it can only be solvated in 1 dimension effectively. And so that dramatically lowers its stability when it's inside the membrane channel. So what we're going to do is we're going to reduce this problem to a discrete master equation description where we have state 0 corresponding to water on the left, state 6 corresponding to water on the right, and states 1, 2, 3, 4, and 5 corresponding to a proton sitting on each of these, on any of these water molecule positions. Okay, so let's go ahead and make our diagram. So we're going to have a state that we're going to call 0. We're going to have a state that we're going to call 1, 2, 3, 4, 5, and 6. And between these, what we're going to do in order to introduce rates for jumping from one state to another, we're going to have a rate to go in the forward direction. That's going to be k plus. And that's going to take me, it's going to be the same rate that takes me from 1 to 2, 2 to 3, 3 to 4, etc. We're going to have a rate k minus that takes me from 1 to 0, 2 to 1. And now there are no rates that take me from 0 to 1 or from 6 to 5. That is because these are absorbing ends. So once I arrive in state 0 or I arrive in state 6, once my proton arrives in there, we're going to assume for purposes of our model that it never comes back. So all we're able to describe is the migration across the channel for a proton that's already in there. When we, if we really wanted to compute the permeability of this membrane, we would need to know how often a proton moves from the bulk into the mouth of the channel. So this transition from 0 to 1, for example, would be a necessary ingredient in a model to compute the permeability. Right now, we're just going to examine the dynamics of a proton moving out of this membrane channel. Okay. If we really wanted to construct a model of the permeability, we would need to include these transitions from 0 to 1, that is a proton entering the channel, and a rate from 6 to 5, which is a proton from the opposite side coming backwards into the channel. These, of course, would have to be rather complicated rate expressions, not just simple rate constants, first-order jumps. These would depend on concentrations of protons, have an electrostatic field imposed across our membrane. The rate constants k plus and the rate constants k minus can be different sizes. And that will give us a bias that will drive protons from one side to the other. All right, so all of these things you can build into the model. We are not going to go into those details today. So what we're going to do now is to develop the master equation. And really, the whole key to building the master equation was this transition matrix. And remember that the transition matrix elements are going to be omega, j goes to I. Now j is going to be the column, and I is going to be the row. So this is a little bit counterintuitive, perhaps, but that's a guide for how to build this transition matrix. In this master equation, we can only make very local transitions, right? So we can only jump from state I to I plus 1 or I minus 1. Okay, since this is our first time, I've written this little table here. So we've got the columns, which are telling us which state we're coming from, and we've got the rows, which are telling us which state we're going to. And now what we're going to do is to fill in, using this diagram, our entire transition matrix W. This is a special case. In this one, it's 0, but it's 0 actually not because we don't have a rate drawn there. It's 0 because there are no rates from 0 to anything else. And then what we're always going to do, remember in the formula for W, is that this ends up being a sum with the opposite sign of all the other rates in that column. Okay, so remember that this is a special case. Now the rate going from 0 to 1 is 0. The rate going from 0 to 2 is 0. The rate going from 0 to 3, etc. I think you guys get the idea. Now I go all the way down here. Hopefully I got the right number of states. No, I did not. I need one more 0 in that thing. All right, so now my first column is finished. Okay, and really what we did was we did all of the off-diagonal elements first, and then we filled in this one. Okay, so let's do the off-diagonal elements going from 1 to other states first. Okay, so those are going to be 1 going to 2 with a K plus. Okay, so this is from 1 to state 2. That's this one. This should have a K plus. And remember that we keep this minus sign in here. So minus K plus. All right, from 1 back to 0, that's this element right here, this is going to be K minus. And remember, because of my convention, we keep a minus sign in there. Now, 1 doesn't go to any other states. So we can take this entire column now and fill in zeros everywhere below. So now let's talk about how we evaluate the diagonal matrix entry. That one is going to be the sum of the other entries. These were arriving in other states from 2, and the flux leaving and arriving elsewhere has to be the flux leaving state 1. Okay, so whatever entries I put off diagonal, I have to have a compensating entry along the diagonal. Okay, let's do this matrix element now. We're going from state 2 to state 0. There are no non-local hops in this transition matrix, so I'm going to get a 0 here. What about 2 going to 1? 2 to 1. Well, I can look at my diagram and I can see 2 to 1 was a K minus again. So that one's going to be minus K minus. And then I also know that going from 2 to 4 is going to give me 2 to 3 is going to give me a K plus again. So minus K plus. And then here, I'm going to get the same thing. All right? So now we have filled in 1, 2, 3 columns of our transition matrix, and you can probably start to see a pattern here. We're always going from, we're always going to get something that looks like this. All right, and we can continue this on down. Let me do dot, dot, dot here. It's a little ridiculous to dot, dot, dot across one thing, but okay. Let's do column 6 first. Column 6 corresponds to a proton leaving state 6 and going somewhere else. Well, it doesn't ever go somewhere else. So all of the off diagonal, those are going to be zeros. Okay, so I can fill in all of these all the way down until I get to the last one as 6. Now, if no probability ever arrives somewhere else from state 6, then no probability leaves state 6, and that's our probability balance idea here. Okay, so now state 5. 5 can jump to 6 with a rate constant K plus. So let's put that one in. That would be right here. We put that in with a minus sign. K minus like this. We have 0, and of course this is going to end up giving us a K plus plus a K minus on the diagonal. Okay, so this is the rate of probability leaving state 5 and the rate at which it's arriving elsewhere from state 5. Okay, so now we're going to remember what we were after here is to get a matrix that describes the evolution of this probability of being in states 0 through 6 as a function of time. This was our master equation. We now have defined our matrix W. It all has constant coefficients. This is a pretty simple one. What we have left to do is, of course, to try to non-dimensionalize this. We have units on the left per time coming from the derivative, and we have units on the right per time coming from the units of the rate coefficients in the matrix. So we're going to non-dimensionalize things. We're going to let this variable theta be equal to K minus over K plus plus K minus. And now we can factor out the K plus plus K minus from the matrix W and write the whole matrix W in terms of thetas. We can also let dimensionless time, tau, be defined like this, okay, in terms of the real time, dt. Okay, so with that in mind, now we get a new equation that will look something like this. So I've, just indicated that my W is going to be non-dimensionalized as well. So my W matrix, after doing this little change, is going to again have 7 zeros down the column. Now we have to start thinking here. So the first row, we factored out a k plus k minus. First element was k minus, so this is going to leave us with a minus theta up here. Okay? The term here, after we factor out a k plus k minus, is going to leave us with a 1. The term sitting here, after we factor out a k plus k minus, is going to leave us with so just the k plus would leave us with a 1 minus theta. The minus k plus will leave us with a theta minus 1. All right, so every single column is going to do something like that. So we have 0, minus theta, 1, theta minus 1, 0, 0, 0. Okay, so this little pattern runs down the matrix like this until we get all the way to the second to the last column. Then we have 0, 0, 0, theta minus 1, 1, minus theta, and a 0 here. And then we have our state 6, which doesn't go anywhere, the absorbing state at the end. And that's our W matrix, now non-dimensionalized. Now this is going to be nice and convenient for doing numerical work of this problem. Okay, first of all, let's sort of sketch what these would mean, right? So if I have a plot, histogram of the probabilities of being in different positions, so I'm going to plot P like this, and the maximum it can ever take is 1. I might have a probability, I might know at the beginning, for example, that I'm sitting in a certain place. And we'll put 0.5 and 0.0 on this plot. We have states 0, 1, 2, 3, 4, 5, and 6. Okay? And let's suppose that our initial conditions are that we start our proton exactly at position 3. So it's the way I drew the picture over here. The proton is starting out exactly like that. All right? So this is my t equals 0 initial condition. Okay, so what this equation now describes is that I'm going to evolve this in time. Okay, so as time passes, the dimensionless time grows from initially 0 up to 2.0, and I'm redrawing my vector at a later time, my vector of probabilities. You see now on a scale from, okay, so we are drawing the case where theta is equal to 1/2. So it's an even split, equally probable to go to one side versus the other with each individual hop. And what happens now is that there's probably a little bit of probability still sitting in state 3, but much of it has now bled out to, dispersed out to other states in my other positions along my pore, including some that has fallen into state 0 and 6, which will never come back, right? So if I continue to advance time, what will happen in the solution to this equation is that my probability vector will gradually get smaller and smaller in state 3 as as probability leaks out through the surrounding states, eventually being absorbed into state 0 and 6, and at very long times with theta equals 1/2, state 0 will capture 1/2 of the probability, and state 6 will capture 1/2 of the probability. Now, if I were to examine a case, if I took a case where theta was not equal to 1/2, then that would tell me, for example, if theta was greater than 1/2, that would tell me that I tend to be biased to jump to the left. And then state 0 would absorb a larger fraction of the original probability than 1/2. It would, I could crank this all the way up so that this almost became 1, and at long times that would basically look like 0. Okay, so this is what the master equation tells you. It builds all of this stuff in. Of course, we can start from things that aren't a sharp initial condition. It can tell you about solutions to those things too. So effectively what you're looking at here is like a Green's function. You're looking at how the probability evolves starting from one specific sharp known state in later time. And we will use this idea of Green's functions as we go on through the course.